Our universe, with its countless galaxies, our solar system, our home planet Earth, the land, the seas, the air, and all life. Where did it all begin? When we look up from our world, we see a vast cosmos filled with billions of stars and galaxies. But rewind the clock more than 13 billion years, and the universe was a completely different place. Back then, it was so incredibly small it could have rested in the palm of your hand. From that infant universe, everything we know would eventually emerge. Stars, galaxies, and the very building blocks of life. The calcium in our bones, the iron in our blood, the atoms that make up the air we breathe, the water we drink, and the raw materials for our cities and machines. Let's take a journey through space and time to explore how the universe was born, how it created everything in our world, and how it will ultimately meet its end. Everything around us is composed of matter, atoms, and molecules. Consider this classic automobile. It's built from various materials like steel, rubber, and glass. Delve deeper, and these materials are made from elements such as iron, silicon, chromium, and carbon. Every single atom in this car was forged by our evolving universe. Physicists explain that the atoms we find on our planet have a cosmic origin. We are partly stardust and partly remnants of the Big Bang. Most atoms in our bodies come from the cores of stars, but some have existed since the earliest moments of the universe's birth. So we are truly cosmic beings. Each atom was created over billions of years as the universe developed. When we look at an object like this car, all its atoms originated from stellar explosions, supernova processes, and stellar evolution, but they were created at different times in cosmic history. To understand how the universe produced all the raw materials we see on Earth, we must travel back through space and time to the very moment of creation. In the beginning, there was nothing, no space, no time. And then there was light. A tiny, intensely hot speck of light appeared. Inside this miniature fireball was all of space. This was the literal beginning of time. The cosmic clock started ticking. Time began to flow and space started to expand. At the earliest instant of the Big Bang, everything in our observable universe, all matter and energy, was once contained in a region smaller than a single atom. Today, the concept that our universe was once minuscule stems from the groundbreaking work of astronomer Edwin Hubble. In the 1920s, most astronomers thought everything visible in the night sky was part of our Milky Way galaxy. But Hubble had doubts. He studied a swirling cloud of light known as the Andromeda Nebula and demonstrated it was actually a separate galaxy, far beyond our own. He also showed that these other galaxies were moving away from us, and the farther away they were, the faster they seemed to travel. The universe was expanding. If the universe is expanding, then in the past it must have been much, much smaller, implying a definite beginning. Thus, the idea of the Big Bang was born. The Big Bang theory is not precisely a theory of how the universe began, but rather a theory of how it evolved from an incredibly early state. No one knows exactly what happened at the very first moment, but scientists understand that a fraction of a second after birth, this super-hot fireball began to expand. We start our story when the universe was almost unimaginably young. It was the size of a marble. In less than a trillionth of a second after the Big Bang, this marble-sized universe was unstable and underwent an enormous, rapid expansion. During this period, space itself expanded faster than the speed of light. Just as a hot glass sphere inflates, the baby universe expanded in all directions simultaneously, cooling as it grew. A trillionth of a second after the Big Bang, the universe was small enough to fit in your hand. A tiny fraction of a second later, it was the size of Mars. Another instant, and it had grown to 80 times the size of Earth. A trillionth of a second after the Big Bang, our newborn universe was still expanding, but it contained no matter, only pure energy. Einstein's famous equation, E equals mc squared, shows that mass and energy are interchangeable. This knowledge led to powerful weapons, but it also revealed how the universe created the first matter. In a nuclear explosion, a small amount of matter is converted into energy. In the baby universe, the opposite occurred. It converted pure energy into particles of matter. However, there was a catch. The universe created both matter and its opposite, antimatter. When matter and antimatter meet, they annihilate each other. The infant universe was a battlefield. If they had perfectly annihilated, the universe would have remained full of energy with no galaxies, stars, planets, or life. Fortunately for us, there was a slight imbalance. For every 100 million antiparticles created, there were 100,000,001 particles of matter. That one extra particle of matter in each volume was enough to account for everything we see in the universe today. This tiny asymmetry led to all the matter we know, from galaxies and stars to planets, automobiles, and ourselves. We are essentially the leftover debris from the annihilation of matter and antimatter. If the universe had not developed this slight imbalance, it would be completely bland, with no structure, no galaxies, and no planets. Understanding what this newborn universe was like has challenged cosmologists since the Big Bang theory was proposed. Now, in one of the world's largest laboratories, scientists can recreate conditions that almost certainly existed an instant after the Big Bang. It's called the Relativistic Heavy Ion Collider, located at Brookhaven National Laboratory. It acts like a time machine, taking us back to 10 millionths of a second after the Big Bang. Here, scientists accelerate subatomic particles close to light speed and smash them together. The particles race around a 2.5-mile circular tunnel in opposite directions thousands of times per second, colliding inside a detector larger than a 3-story house. When they collide, they generate incredible heat, similar to the real infant universe. The early universe was extremely hot, billions of times hotter than the sun's core. By smashing these nuclei together, scientists melt matter, creating conditions hot enough to glimpse the very early universe. When the particles collide, they break apart, releasing a shower of even smaller particles. It's like discovering what cars are made of by crashing them together repeatedly. You start to see different parts emerge. What scientists at Brookhaven discovered is that within these superheated collisions, a completely new form of matter appears, contradicting previous theories. It's not a gas, it's a liquid. It was super hot, 100 million times hotter than the sun's surface. There was so much energy that particles vibrated extremely fast, with no stickiness or friction, flowing perfectly. This liquid had no viscosity. In a sense, it would be the perfect motor oil, except it was 1 trillion degrees hot. Inside the collider, this amazing liquid universe exists for only a tiny fraction of a second. The scientists have succeeded in recreating conditions from over 13 billion years ago. Despite being a perfect liquid, the universe was in turmoil, full of subatomic particles smashing together and releasing energy. There was so much energy that unless the particles slowed down, they would never bond to create atoms, the building blocks of matter. Without atoms, the universe could never create galaxies, stars, or us. The universe is now 1/1,000,000th of a second old and has expanded from smaller than an atom to 8 times the size of our solar system. After the incredible turmoil of the first millionth of a second, the universe became relatively calm. Over the next 3 minutes, the expanding cosmos cooled enough for protons and neutrons to bind, forming the first atomic nuclei, hydrogen and helium. These were not yet complete atoms. They were missing electrons. In the hot baby universe, electrons were present but moving too fast to form bonds due to the intense heat and energy. This state would last for over 300,000 years. 380,000 years after the Big Bang, the universe had expanded to the size of the Milky Way. It had cooled from billions of degrees to just a few thousand. As it cooled, electrons slowed down. The universe was now ready to make its first true elements. One of the scientists who discovered this critical moment was working with a new antenna. Initially studying cosmic radio waves, he and his colleague detected an unexpected background noise that seemed to come from the sky. They carefully eliminated all possible sources, including ground interference, solar system effects, and man-made signals. In desperation, they even considered pigeons roosting in the antenna as a source. But after cleaning it and removing the birds, the mysterious signal remained. They were left with the almost inescapable conclusion that this radiation was coming from the sky. This strange signal turned out to be one of the most important scientific discoveries of all time. But the explanation starts not with sound, but with the birth of light. We often take light for granted, but in the early universe 13 billion years ago, we would see nothing. Light was trapped. The universe was foggy. Imagine a flashlight beam in thick smoke. The light bounces around and can't escape. In the hot baby universe, a dense fog of electrons blocked light. But as the universe expanded and cooled, electrons slowed down. Protons then captured these calmer electrons to form complete hydrogen and helium atoms. Suddenly, the universe was much less crowded with electrons. The fog lifted, and light was no longer trapped. It hurtled across the universe in a blinding burst. Had we been there, we would have seen this opaque universe become transparent in an instant. It must have been spectacular. Over time, this burst of light dimmed and cooled, becoming microwave radiation. It was this faint, 13-billion-year-old microwave signal that the scientists detected. What they heard was the quiet echo of the moment the universe formed its first atoms. It is the light from the origin of the universe. If you have an old FM radio and tune between stations, you hear static. A tiny fraction of that noise is actually the sound of the Big Bang. We can also witness the moment the first elements were created. On an untuned television, a small part of the snow is radiation from 13 billion years ago. This radiation isn't the only reminder of the universe's birth. Even the water we drink contains atoms that have existed since the Big Bang, the hydrogen atoms. Over the next millions of years, the young universe continued to expand, cool, and grow dark again. So far, it had only produced hydrogen and helium atoms. But our world is made from more than 100 different elements. Without them, the universe would remain a boring place of only gas, where complex matter like planets, cars, and people could never form. The universe needed to fuse hydrogen and helium atoms, and to do that, it needed to make stars. The universe was now 200 million years old and billions of light years across. Its temperature had dropped far below freezing, colder than liquid nitrogen. It was also dark. It would have stayed a gloomy place full of gas, without galaxies, stars, or planets, if not for one thing. The baby universe wasn't born perfectly smooth. Amazing 3D simulations show that when the universe emerged from the Big Bang, it was uneven. Tiny cracks appeared, and these minuscule imperfections later developed into the patterns we see in galaxies today. Without these cracks, the universe would have been very dull. The first clues about how these cracks developed into galaxies and stars came when scientists examined the Big Bang radiation first discovered. Initially, this radiation appeared uniform. For the next 25 years, cosmologists worked hard to find tiny variations, and they succeeded using a space probe designed to detect and analyze detailed variations in the background microwave radiation. Launched in 2001, this probe was fitted with some of the most sensitive instruments ever sent into space. Our eyes see only visible starlight, but this probe could tune into invisible microwave radiation. From orbit around the sun, it picked up faint radiation that has been traveling since the dawn of time. When we look at this cosmic background radiation, we are seeing light that has been streaming toward us since 500,000 years after the Big Bang. At first, the microwave universe looked dull and uniform, but when contrast was enhanced, the results were spectacular. The baby universe wasn't smooth at all. It was full of fluctuations. These tiny variations tell us about differences in density, how much material exists, and how it varies from place to place. Denser regions would collapse to form clusters of galaxies, superclusters, and galaxies themselves. Low-density regions would become the empty voids between galaxies. 7 billion years old, these tiny imperfections in the fledgling universe would become galaxies and stars. It's one of the most amazing ideas in physics, that galaxies like the Milky Way, containing hundreds of billions of stars, began as tiny cracks in the fabric of the universe. Material in these cracks consisted of swirling clouds of hydrogen atoms. The voids between clouds grew larger, while the gas clouds became denser and hotter. Gravity pulled the gas clouds together along filaments, like beads on a cosmic web. Where giant filaments formed large globs, stars and galaxies would grow. As the universe evolved, gases condensed into clouds that collapsed to form stars. The stars settled into rotating disks that later became spiral galaxies like the Milky Way. Over millions of years, hydrogen atoms clumped together and heated up. Atoms began fusing, releasing energy, and the gas cloud started to burn brightly. Eventually, a star was born. All across the universe, millions of stars ignited for the first time. The appearance of the first stars would have been a truly spectacular event. Had we been there, we would have seen enormous flashes of light as stars were born. The universe had expanded trillions of times its original size. It was filled with newborn stars made of hydrogen and helium. These young stars were very unstable, unlike our sun. But their instability made the universe more interesting because deep inside each new star, something amazing was happening. They were creating new elements. The idea that stars build atoms came from a renowned British astrophysicist. He didn't believe the universe began in a single explosion. In fact, he coined the term Big Bang somewhat mockingly. He wanted to know where elements heavier than hydrogen and helium came from. He figured out that stars act like nuclear reactors, similar to a hydrogen bomb in slow motion, but billions of times more powerful. Their nuclear waste was new elements. It took years before scientists could confirm his theory by analyzing starlight. Each element emits light at a specific frequency when heated. Think of a sodium street lamp emitting its characteristic yellow light. It's the same with stars. Our sun's light, when broken into a spectrum, shows lines like a barcode corresponding to different elements. Each element has specific colors, helping scientists identify them. In 1990, NASA launched the Hubble Space Telescope to unravel mysteries of the early universe. It promised unprecedented views of the young cosmos, able to look back through space and time to examine early stars and see if they were making new elements. But soon after launch, a nightmare unfolded. Hubble's mirror was distorted, making everything out of focus. It needed corrective lenses, requiring another space shuttle mission. Astronauts, including a key repairman, had to capture the crippled telescope and execute an unprecedented repair in space. Working in bulky spacesuits with stiff gloves was like working in ski mittens, a significant challenge. After 5 days of meticulous work, the repairs were complete. Cosmologists worldwide waited anxiously. On New Year's Eve 1993, the call came. The first picture was back, and Hubble worked. The images were beyond anyone's wildest dreams. Hubble captured the final moments of stars exploding, interstellar nurseries of newborn stars from billions of years ago, and dark pillars of cosmic dust millions of miles long, ready to spawn new stars and planets. One iconic image, the pillars of creation in the Eagle Nebula, shows the birth of stars in an almost biblical way. But Hubble's true moment of glory was still to come. Over 10 days in 1995, mission controllers pointed the telescope at a seemingly empty patch of space. The resulting deep field image revealed a tapestry of distant galaxies. Hubble was looking back in time to some of the first galaxies and stars ever created, showing thousands of previously unseen galaxies. The universe became far richer in our consciousness. It showed faint images of galaxies formed just a billion years after the Big Bang. Scientists then examined the light spectrum from these distant stars and found that these early galaxies had already created elements heavier than hydrogen and helium. The scientist who proposed stars as element factories may have been wrong about the universe's birth, but he was absolutely right about stars. Early stars acted like giant thermonuclear reactors creating new elements. Think of it like a car assembly line, where each part is added sequentially until the vehicle is complete. Fusion reactions inside these young stars released enormous energy and heat, forcing atoms to fuse and form heavier elements one after another. 3 helium nuclei combined to form carbon. 2 carbon nuclei fused to form magnesium, magnesium to form neon, and so on over hundreds of thousands of years until silicon fused to form iron. Iron is special. The protons and neutrons in its nucleus are so tightly bound that even extreme stellar temperatures couldn't fuse it into heavier elements. The production line shut down, but the universe was still incomplete. There were ingredients for water and some elements for a car, plus many for a human being. The oxygen we breathe, the calcium in our bones, and the iron in our blood. Yet vital ingredients like chromium for car fenders and essential metals like zinc were still missing. The universe was about to enter a super-creative phase, producing all elements heavier than iron. To finish, the cosmic jigsaw required some of the most powerful explosions ever: supernovas. Our universe was now 500 million years old, with 13 billion more years to go before humans appeared. Giant new stars had made many elements, but some heavy metals like chromium, zinc, gold, and platinum were still missing. To finish the job, the universe conjured up massive exploding stars called supernovas. When giant stars that made lighter elements ran out of fuel, they collapsed, creating incredible energy and enormous explosions. These explosions were so powerful they could fuse elements heavier than iron, restarting the element production line. Without these exploding stars, life as we know it would not exist. They are a key link in our chain of origin from the Big Bang to today. One of the closest and biggest recent supernovas was observed in 1987. When a supernova explodes, it emits light containing signatures of its elements. By examining this light spectrum, scientists can determine what elements are being forged. Researchers recreate these events in laboratories, accelerating and smashing particles together, simulating conditions inside a supernova. These experiments measure how fast nuclei fuse, translating that information to understand processes in exploding stars. In extreme conditions, particles fuse, allowing the formation of elements much heavier than iron, all the way up the periodic table. Massive stars evolve into an onion-like structure at the end of their lives, with an iron core surrounded by layers of lighter elements. Inside the iron core, temperatures rise to 8 billion degrees, nearly 300 times hotter than the sun's center. It's so hot that iron atoms are torn apart. The core destabilizes and collapses in a fraction of a second at speeds over 43,000 miles per second. A volume the size of Earth crunches down to nearly 6 times the size of Manhattan instantly. The core becomes super dense. A sugar cube-sized piece would weigh as much as all humanity. The core rebounds like a compressed rubber ball, launching a massive shock wave. This shock wave smashes through the star's outer layers, generating energy that restarts the element production line. Atoms are smashed together to create brand new, heavier elements. Then the star explodes, pushing debris outward into space. Our lives depend on the stars. Without their lives and deaths, we wouldn't be here. Hubble images show the aftermath. Nebulae, giant clouds of debris from exploding stars. Swirling inside are new atoms like gold, silver, zinc, and lead. Without supernovas, our world would be dull and possibly lifeless. All the bling and precious metals owe their existence to these cosmic explosions. 9 billion years after the Big Bang, all ingredients for life were in place. The universe had grown into a vast, complex place of billions of galaxies and countless stars. In a quiet corner of the Milky Way, a mass of dust and gas began to accumulate, rich with debris from a supernova. When it reached critical mass, it began to burn brightly. A star was born, our sun. Leftover material formed a swirling disk orbiting the new star. Gas and dust in this ring collided, pulled together by gravity. Clumps grew larger, forming planets. One of these planets was Earth. Over the next 500 million years, Earth developed a protective atmosphere. The first life appeared, single cells that eventually evolved into plants, animals, and humans. We often disassociate ourselves from the universe, but that's wrong. We are a vital part of the cosmos. When we discuss the origin and evolution of the universe, we're talking about our own origin and evolution. Everything on our planet was made either in the Big Bang or inside a star. Scientists believe they now know the genesis of every atom in our world. These atoms have existed since the dawn of time. But this isn't the final chapter. After almost 14 billion years, the universe has only just begun. Now, let's journey into the future to see how it all ends. The universe is nearly 14 billion years old. It has created raw materials for everything: stars, planets, trees, cities, automobiles, and us. Our world is complete, but the universe is still evolving. Scientists have many theories about its end. We know it began with a Big Bang, but the future is uncertain. It may end with a bang, a whimper, or something more exotic. One theory suggests the universe will run out of steam, stop expanding, and collapse into a superdense point called the Big Crunch. To determine if the universe will collapse, scientists need to know if it's still expanding or slowing down. Astrophysicists study beacons in space, Type 1a supernovas, exploding stars. By measuring their brightness, scientists can determine distance. Fainter supernovas are farther away. Type 1a supernovas are special because they always explode with the same brightness, as they form in the same way. Two stars orbit each other, one a white dwarf, the other a red giant. 44 times the sun's mass, then collapses and explodes. Every Type 1a supernova explodes at this tipping point, making them equally bright across vast distances. Researchers hunt for hundreds of these supernovas using powerful telescopes on Earth and in space. Once a supernova is detected, its light is broken into a spectrum to confirm its type and calculate distance. By comparing positions and dates of many supernovas across space and time, scientists can determine if the universe's expansion is slowing. The results were shocking. The expansion isn't slowing down, it's speeding up. This means the universe will not crunch back into a superdense point. Instead, it will continue expanding faster and faster, flying apart. The expansion will accelerate until everything is ripped apart. Not just galaxies, but eventually matter, stars, planets, people, and even atoms. Long after our sun burns out, 100 billion years in the future, galaxies will pull apart. The universe will consist of isolated stars running out of energy, becoming white dwarfs, brown dwarfs, neutron stars, or black holes. Thousands of trillions of years after the Big Bang, even black holes will evaporate, and all matter will decay to basic ingredients. Atoms will fall apart, and protons, the building blocks of atoms, will decay. The most likely future is a dismal one, where the universe becomes cold, dark, and empty. As galaxies speed apart faster than light, they will disappear from view. Everything will wind down, and the universe will die, leaving only cold, dark, lifeless space. If you enjoyed this cosmic journey through time, make sure to subscribe for more explorations of the universe's greatest mysteries. Don't forget to like this video and share it with anyone curious about where we come from and where we're headed. Your support helps bring more stories like this to light. Thank you for watching. Video and share it with anyone curious about where we come from and where we're headed. Your support helps bring more stories like this to light. Thank you for watching.